Okay, so we're on journal 48, and we're going to start with Bellwork. So in this Bellwork, we're going to be graphing an exponential and a log, and we're going to put them side by side to see what can we find that are similar and what can we find that are different. So let's refresh ourselves on how to graph an exponential function first. So here I have 3 to the x, and if I were to graph this, well, let's first start by answering what the asymptote is. So looking at this function here, my base is 3, but it doesn't look like I have an asymptote, right? Because if you remember, in one of the first videos, we talked about exponential functions. And exponential functions have generally a coefficient with a base to the power x, and then plus k, or sometimes it's minus k. And so the k represents our asymptote. So in this case, notice that there isn't a plus or minus anything next to the base. So in this case, our asymptote is at 0. So if you don't see a k, the asymptote is 0. And if you remember, this type of asymptote is a horizontal asymptote. Okay, now let's talk about domain and range. For exponential, it's the domain that's all real numbers. And we'll see why here after we make a table. So let's make a table here. So if you remember, when we make a table, we have to plug in values for the exponent. Our exponent here is x. So I'm going to choose my typical -1, 0, and 1. If I plug this in for the x, let's see what we get here. This would be like 3 to the -1. 3 to the -1 is like 1 over 3. Remember, this here is a negative exponent. So what do? You flip this 3. So in this case, think of 3 being 3 over 1. Well, if you flip it, that's 1 over 3. So in this case, we have 1 over 3. Or you can write that as a decimal, which is 0.33. Okay, 3 to the 0, if I plug in the next x value, is just 1. Anything to the 0 power is just 1. And lastly, 3 to the first power is 3. And so now we're going to plot our point. Now remember, the horizontal asymptote here is at, so you would go to the y, and you would go to 0. So here is our horizontal asymptote. Now, I'm not going to actually highlight or do a dashed line for the horizontal asymptote because I'm going to be drawing 2 lines here and I don't want it to get confusing. So I'm just going to plot my points, but I'm just going to remember that this here is my horizontal asymptote, so I don't want to touch that line. So if I were to plot my points here, it would be, let's see, -1 up 1/3, which is like right about there. 0, 1 is right about here, and 1, 3 is like right there. So I'm going to connect the dots, and this I'm going to do my very best not to touch that line. Okay, got it. So when I look at this here, notice that the range is from 0 to infinity, right? Because this curve gets really, really close to the horizontal asymptote, but not quite. But on the other side, it does go up. So we're going from 0 to infinity. Now, I was talking specifically for y values. So the horizontal asymptote kind of cuts off the y values from going any further than 0, y equals 0. All right, let's take a look at the log function here. So if you remember when we were graphing logs, here's the thing. With logs, we can't graph them. So what we have to do is we change them to exponential. So let me write a note here. So to graph logs, you have to change to an exponential form. So in our case, this problem here, to change this to an exponent form, you can, rewrite it, figuring out the base, the exponent, and the value. Or you can use the heart method. To do the heart method, you have to make sure that the log is on the left-hand side. So let's rewrite this function where the log is on the left-hand side. And here we have it. So now we're going to make our heart. So we're going to go 3 to the y. So that's going to be 3y. And then we land on x if we complete our heart. So this equals x. And notice that x is by itself, which is good. So when I look at this side of the equation, notice that you just have 3y. There's no k value. So in that case, our asymptote is at 0 because there isn't a k value there. The domain here, not sure yet. I haven't plotted points, but the range here is all real numbers because for logs, they're all real numbers. So let's figure out what the domain is. So I gotta pick some x's and y's. So when I'm trying to plug this into the equation, you might want to choose y values because in this case, y is your exponent. So it's easier to choose y values. So if I chose y values like -1, 0, and 1, like my typical ones, if I plug this into the -1, 3 to the -1 gives me let's see, let's do that to the side here. Three to the -1 is 1/3. So that's 1/3 right here. And then 3 to the 0 is 1. And 3 to the 1 is 3. Hey, wait a minute. Aren't these values just the values that we got a moment ago in the other table? But they were for the y values? Interesting. But let's plot our points. So it looks like we have 1/3, -1. Sorry for yawning. It's actually really late right now that I'm recording this, so bear with me. So we have it at -1 and then 1, 0. And then 3, 1, which is right here, and I'm going to connect the dots. But remember, we have a vertical asymptote because this is a log equation. So logs have vertical asymptote, and in this case, it's at 0. So on the x-axis, I'm going to go find x equals 0, and imagine that there was a vertical asymptote right through here. So you don't want to cross it with this curve, so it's going to curve this way, but it gets really darn close to this line right here, the y-axis line. So on here, I'm going to curve, and looking at this here, let's figure out our domain. So our domain here is going from, looks like 0 to infinity. And that's it. So notice how like these two graphs, let's take a look at their similarities here. We can see that their domain and range are switched, right? Like this is all real numbers for the domain, but that's all real numbers for the range, where the domain and range for these two are switched. You might also notice that their asymptotes are the same, right? So let's just talk about domain and range being switched. So whenever you switch the domain and range, that's like saying you're switching the x's and y's. And where have we done this before? Well, we've done this before when we try to find inverses. So when we look at exponential functions and log functions, they're inverse of each other, and you can see that here based off the tables, right? When you look at the x values, they're actually the y values, where the x values are actually those y values. So inverses, when you look at the graph, they have this special characteristic. Basically, they are a mirror image across this line that I'm about to draw in red. So if you were to think of this as a sheet of paper and you were to fold it diagonally in half, like perfectly, this curve would be a reflection of this curve, or they would be on top of each other if you were if you had the paper folded. So this is a big characteristic for functions that are inverses of each other. They have this reflection across this diagonal line here. Okay, so we just talked about how logs and exponentials are inverses of each other, and also they can be used to cancel each other out when they have the same bases. So just like how multiplication does division, we can use logs to undo exponents, or use exponents to undo logs. but here's the caveat: it has to have the same bases. You might have seen in the first Bellwork, the Bellwork in the previous slide, both of the equations had the same bases. They were both 3's. So in this here, notice that when I look at this here, this is a exponential form where the 14 is the base and the log 14x is all the exponent. Whereas log 14, this one here, it's the log now in front, so we're taking the log base 14, and then this here, they plugged in 14 to the x, so that's their value. And so when you look at this here, whenever you have the same bases, they cancel each other, leaving you with only your value, in this case, whatever's inside of this log left, which is just x. Okay? So notice that when you cancel, it takes the 2 bases and also a log. So that's kind of nice. And the next one here, we have a log in front, but there's a base of 14, and then there's a base of 14 on the exponential. So they cancel, giving you just x. And that's it. Okay, next thing we're going to do is simplify the expression using that inverse property that we saw a moment ago. So remember, if the bases are the same, then they cancel. And so in this case, for part A, notice that you have a base of 6 and the log base is 6. So in this case, they're going to cancel. And so if they cancel, that means I'm just left with 7x. So in this case, this answer here is just 7x. And we're just simplifying here, so 7x, I can't really do much more than that. So this is my answer. Let's try B. So B here, notice that the base of the log here is 4, but this base for the exponent is a 64. Now these two definitely aren't the same bases. So what we have to think about is maybe manipulating this exponent base to make it look like 4. So let's think about it. If the base for the log is 4, right, and we want this to equal 64, then what does my exponent for this 4 need to be to get 64? Well, if you remember, 4 to the 3rd power gives me 64. So what I can do is I can change this 64 to a 4 to the 3rd power. So what I'm going to do is I'm going to rewrite this function log 4, but instead of a 64 here, I'm going to replace that with 4 to the 3rd power. Now, there was a x here, right? So in that case, I need to write back that x to the side. Let me do this in black here. So the original problem, we had log to the 4, and we're replacing this 64 with 4 to the 3rd power because that's still 64. And then there's still an x in that exponent, so I'm going to write that there. And so when we work out this problem, well, now the bases are the same. They're both 4, so they cancel, leaving you with just, looks like 3x here. So it looks like my value here is just 3x. And that seems to be simplified, so I can't do more than 3x. Okay, let's look at this problem here. So part C, notice that this log doesn't have a base here. So by default, the base is 10, if you remember that from our last video. But here we also have the exponential, which is 100, right? So these are not the same bases, but I think I can make 100. Let me do that in green. So I think I can turn 100 to a base to a power, right? So I can write 100 maybe to the 2nd power will be 100, right? 10 times 10 is 100. So what I can do is I can make this look a little different. I can do log base 10, but instead of 100, let's write it as 10 to the 2nd power. Right, because that's still 100. And then there is an x for the exponent, so I'm going to put that there. And so now my bases are the same, so they're going to cancel, leaving me with just 2x, it looks like. And that's it. And then let's take a look at part D. So part D, we have a base of 10. And this log here doesn't have like a little base here, right? So in this case, the log has a base of 10. So we have 10 log base 10 and then a 5. Oh, would you look at that? When I wrote that 10 in, it looks like these bases are going to cancel, leaving me with just 5, it seems. And that's it. So whenever the bases are the same, they cancel. And also takes the log with it too. So notice that when you cancel, the log also cancel along with it, right? Okay, and if the exponent here is not the same as the base of the log, what you have to do is take the exponent and manipulate it to make it look like the base. So take the base and set it equal to the value and figure out what exponent makes it that value. That's it. Okay, so let's take a look at our next example here. Okay, now we're going to be finding inverses. So to find the inverse of an equation, remember, we switch the x's and y. That's like the very first step we do. So we're going to switch x and y, because that's what it means to take an inverse. So here I go. I just switched x and y. And then once you switch them, notice that the y is not by itself anymore like it was in the beginning. So what you have to do is you have to solve for y. So you have to get y by itself. But how do I get this y out of this log? Well, it looks like in order to get rid of a log, we learned that the inverse of a log is exponent. So what we have to do is change this log to an exponent. Okay, so before we try to do that, let's first look at what the base of this log is. Notice that this log doesn't have a base, so by default this log has a base of 10. And so what you have to do to change this log to an exponent is to rewrite it as an exponent. So one way we can do that is to use the heart method. And so to do that, the log needs to be on the left-hand side. So I'm going to rewrite the log so it's on the left-hand side. And now I'm going to do my heart method. So it's going from 10 to the x to the y. So this is, 10 to the x equals y. And notice now my y is by itself, so y is solved. But this is an inverse. So that means that this is not the original y. This is the inverse y. So what you have to do is write it as y negative 1 equals 10 to the x. So you have to use this negative 1 exponent on the y to say that this is the inverse of y. Remember when we used to write, like we would start out with a function, and then the inverse of that would just be f negative 1 f of x. This would say this is the inverse of the original function. Well, that negative 1 there symbolizes that. So make sure that you write that negative 1 once you solve for y. Okay, let's try another problem here. So like for b here, you have, so the first step for finding inverses is that you switch your x's and y. So let's go ahead and do that. Okay, so now we're going to try to solve for y, and here's y. So the y is inside the log. So what you have to do is try to get this log by itself first. So you want to get the log by itself. Well, notice that the plus 2 is not inside the logs. If it was, then you would have seen this in parentheses, but you don't. So what you have to do is you subtract off the 2 to get the log by itself. 2's cancel. So I have x minus 2 equals log 4y. And now you have the log by itself. And so if you want to get this y outside of the log, well, that's back to this problem here. You have to switch this log to an exponential. So let's write that log on the left-hand side so we can do our heart method. And so in this case, we're going from the 4 to the x minus 2. So that's going to be 4 to the x minus 2 equals y. Notice that y is now by itself. And so now the last thing we have to do is make sure we state that the y is an inverse. Now you do not need to rewrite the equation like I did in the first one. I just did that to show that as an example. But once you solve for y, if you want to just put a -1 as the exponent to say that this is the inverse, you are fine to do that. You don't have to rewrite the equation. Okay, so we're done with B. Let's try out C now. So C here, we actually start out with an exponent, and we're going to try to find the inverse of that. So very first step is to switch the x's and the y's. Okay, next step is to try to get the y by itself. So how do you get this y out of the exponent for this base here? Well, in order to do that, you will need to change it to a log. So when you have a log, you want to change it to an exponent. When you have an exponent, you want to change it to a log. So what we're going to do here is notice that the exponent here is on the right-hand side. So to do a rewrite, you can also still use the heart trick. The only thing is that the exponent needs to be on the left-hand side, just like how the logs needs to be on the left-hand side to do the heart method. So I'm going to rewrite it as 3 to the y equals x. So I've just switched the sides. And if I use my heart method, I'm going from 3 to the x to the y. The only thing is I want to write log first and then fill in my things. So this is going to be 3 to the x. So this x here is the value equals y. And notice that now y is by itself, which is good. And so now to say that this is the inverse, I need to write that -1 for that y to say this is the inverse of y. And I'm done. Last but not least, we have D. We're going to do the same thing. We need to take a look at this equation. But before we do that, let's switch our x's and y's. So I've just switched them. And so when I look at this equation here, just like the logs, you want to get the exponent by itself before you try to switch it into a log. So notice that this exponent here is just the 2y, right? So I want to get the 2y by itself. So I'm going to add the 5 over. So if I add the 5 over, 5's cancel. So I just have x plus 5 equals 2y. And so in order to get this y out down from the exponent, you got to change it to a log. So I'm going to rewrite the exponent where the exponent is on the left-hand side so I can do my heart trick. Okay, so we're going from the base to the value to the exponent. So this is going to be log base 2 to the x plus 5. So I'm going to put the x plus 5 in a parentheses, and then it goes to y. So when I look at this here, y is now by itself. So I just need to top this off by putting a -1, and that's it. So this is the inverse function for our logs. Okay, last but not least, this last slide here, we're going to be solving for x. So that just means I need to get x by itself. So here's some tips here to how to do that. What you have to do is rewrite the function as an exponential form. Notice that I have these all in logs. So we're going to switch them to exponential, and then we're going to try to solve for x. So with this one here, notice that the log here is already written on the left-hand side. So this is a perfect setup to do the heart hack or trick. So we're going to start from the base to the 3, and then looks like it lands at x minus 5. So this is 2 to the 3rd power equals x minus 5. So when I look at this, this is just an equation where I want to try to get x by itself. So let's try to simplify this. Like 2 to the 3rd power, that's like 2 times 2 times 2, which is 8. And then I have x minus 5, so I have to get this x by itself. So it looks like I'm going to add over 5. That cancels. 8 plus 5 gives me 13. So it looks like x equals 13. Now, hold up. This is a log problem, so make sure that you double check whether this statement's true. So you want to plug 13 back in to see if that doesn't give you any negative numbers. So if you plug 13 back in, 13 minus 5 gives you, what, positive 8. So it looks like 13 checks out. So as long as you don't get, so remember, logs, with whatever base it is, you don't want the inside to be a negative number. or 0. Okay, if it is, then there's no solution or it's undefined. So let's try B. So we're going to do the heart trick. So we're going from 3 to 5. So this is going to be 3 to 5 equals 9x. Well, 3 to the 5th power here, I believe, is 247. And that equals 9x. And then I would have to divide everything by 9 to get the x by itself. So that cancels. So 247 divided by 9 is 21. So that equals x. And so if you plug 21 back into here, 9 times 21, that's still a positive number. It's not going to be a negative number. So it looks like this value checks out. So last but not least, we have part C. So we're going to go from the base to the 4 to the 625. So this is going to be x to the 4th power equals 625. And so now we have to try to get rid of this, get the x by itself. So we have to get rid of this power. Well, how do we get rid of powers? Well, we learned in the last unit that to get rid of a power, you take a root. So I need to take the 4th root to get rid of the 4th power. So I have to take the 4th root of the other side. So the roots end up, and the power ends up canceling. So I just have x equals, okay, so the 4th root of 625 is, if you put that in the calculator, it is 5. So if you multiply 5 4 times, you get 625. So you would double check if this value is true, but hold up, you would actually just plug this into the base. So the base can be whatever value it wants to be. So this is a fine answer. So there's no issues with plugging in 5. Because remember, it just has to be that the inside the parentheses needs to be not a negative number or a 0. So 625 is a positive number. So there's no issues here. All right, that's it for this journal and this unit.